Hi, and welcome back. This is lecture 1 of 3 on Chapter 10. Now, Chapter 10 introduces us to the concept of rotational motion. Now, I'm going to warn you, the next 3 lectures are going to be pretty dense, but thankfully, much of what we're talking about, or much of what we're going to talk about, rather, is going to be incredibly similar to what we've seen before. Specifically, material from Chapter 3 in rotational motion resembles motion along one direction. So that said, to show you a reason as to why we need to talk about rotational motion, I want you to think about, I don't know, some ball floating around in space like this. Now, when you add structure to something, specifically it has a spherical shape like this, what that does is to affect how interactions with it play out, if you will. So, for example, if I push this thing dead center straight on, we would expect the ball to move like this. But if I were to push it just a little ways up like this, the ball might still have some side to side motion, but it'll also start to rotate as well. So when you add structure, when you add shape, if you will, to something, what you do is you add another layer of complexity to its behavior. But that's okay. Remember, way back when, I'd say back in chapter 3, when I first started talking about concepts like position, displacement, velocity, acceleration, and what have you, I set down some conditions that I told you that we were going to eventually relax as we went through the course. You have to start easy, and then you add on more levels of detail. And this is another level of detail. So, that said, let's talk about some of the complexities. And some of those I'm going to show you through a simple example dealing with a composite object. So, I want you to imagine an object that's made out of 3 masses that are attached via massless rods like this. So this is mass 1, this will mass 3, and this is mass 2. Now, first of all, the object can't flex. If it flexes, then the description of the behavior of this thing as it rotates is incredibly difficult. Secondly, we're going to treat it as though it's a rigid object. We call them rigid rotators. Okay? So the point that this thing is going to rotate about is right here. I'm going to call it P. And we'll have it rotate this way. Okay, so around like that. Now, so let's talk about the individual velocities of these masses as they move through space, as this thing rotates. So if we look at mass 1, okay, and you think about its, we'll just say speed, actually. Well, we know speed is distance over time. As this thing rotates, the shape that it's going to trace out as it does rotate is that of a circle. So one rotation would be one circumference, or 2 times pi times r1. Now, we'll say that happens in some amount of time t. Now, object number 2, as it rotates, is also going to trace out a circle as well. Its circle is going to look like 2 times pi times r2, traced out in the same amount of time that it takes 1 to go around once. Object number 3, its speed is going to look like this. One circumference over the same amount of time that it took 1 and 2 to do their thing. Now, R1 and R2 and R3 are all different lengths. Okay, R1, R2, and R3. And as a consequence, what that means is that as this thing rotates, their velocities are all going to be different. Now, that's pretty complicated if you think about it. So what I'd like to do is, instead of thinking about the velocities of these things as they go through space, what I'd like to do instead is to think about the angle that they sweep out. You see, because this is a rigid body, what that means is that M1, M2, and M3 all sweep out the same angle over time. If this thing goes around 2 pi radians in 5 minutes, this is going to go around 2 pi radians in 5 minutes as well. And so is this. So whereas their physical velocities, we call them tangential velocities, are all different, their angular velocities are all the same. Now, because of this, when it comes to describing rotation, we like to talk about angular motion as opposed to traditional motion that we've talked about in the past. So the preference is angular motion. We call it translational motion. That's point A to point B in space. So, for example, you could have something move, from here to here. We'll say a cube or something like that. Here's a cube. So it could move from point A to point B in space, and that's translation. But as it moves, it can also rotate like this, and that's rotation. So you have two unique types of motion here. When put together, that describes the full motion of something as it moves. Okay. Now, so that said, because we're dealing with angular stuff, let's examine the coordinate system that we typically use, and we may have to make some changes there. Now, in the past, what we've done is we've dealt with standard Cartesian coordinates. So standard Cartesian coordinates, you have z, you have y, you have x. And if you were to locate a point in space here, which I'll call P, it has an x coordinate, it has a y coordinate, and it has a z coordinate. Okay, so here's us locating using a vector r. So this is Cartesian coordinates. Now, so to start off easy, instead of talking about 3 dimensions like that, let's just talk about 2, and let's talk about motion in the circle. All right, so there's a circle. Center this right here. Now I'm going to still put, y and x here. Here I am locating something that's moving right here around the point here, so it's rotating around it like that. And if you look here, you have an angle, theta, and then you have r, which locates this. We call these, circular polar coordinates. And when it comes to rotations, especially two-dimensional rotation, which is primarily what we're going to be dealing with, this is the way to go. Now, the reason is because as this thing goes around in a circle, its x position and its y position are they're all functions of time. So x and y are continuously changing. But here's the deal, though. With a circle, the radius has a constant length. And the way you locate something is through angle and radius. Okay? So what that means is that your radius itself, the length doesn't change, but theta might be a function of time. So instead of having two things that continuously change, here you have one thing that continuously changes, which is incredibly convenient. So circular polar coordinates, when it comes to dealing with simple rotational motion like this, definitely the way to go. Now, there are other coordinate systems that we look to in order to talk about rotational motion. Like I said, circular polar coordinates is what most people are familiar with through things like trig. But you also have something called spherical polar coordinates. Spherical polar coordinates look like this. You have z, y, and x. Let's pretend that I'm locating something over here, we'll say. And what I'm going to do is I'm going to project the location of this thing down into the xy plane like that. So you can kind of have a little sense of depth there. And so this might be the vector that locates this thing's position in space, but the coordinates would be theta, phi, and r. Okay, so here r, theta, and phi would be how you would locate it. We're not going to be doing much at all with spherical polar coordinates, simply because the first place you typically see these things to any great detail would be in Calc 3. All right, so it requires a much broader understanding of calculus. So another coordinate system that you see used is something called cylindrical coordinates. So let me draw a coordinate system here real quick. Like that, your axes, here's z, here's y, and here's x. Let me draw sort of the circular path that this thing takes as it goes around, we'll say. Whoops, it's like that. And, maybe we'll locate it up over here like that. And you project this down here. Now, so typically where you see cylindrical coordinates used is when you have something that moves around in a circle, but also moves up and down like a helix. Later on, we'll be talking about magnetism. That's University of Physics 2, and that this is the type of coordinate system that you would use when you deal with stuff like that. But I don't know why this did what it did, but anyway, you would locate things with respect to theta, with respect to what we call rho, and then z is how high above. Rho is kind of like r for circular polar coordinates. Okay, so you have spherical polar coordinates, you have circular polar coordinates, and then you have cylindrical. Now, primarily we're going to be using these. Okay, simply because of the motion that we're looking at, we want to keep relatively simple. So that said, I want you to think of something moving around in the xy plane. I'm going to add a z coordinate to it because it helps to add depth. Okay, so here's z, here's y, here's x. Okay, and we'll say here's the path that this thing takes as it goes around in a circle. Actually, I want to be, again, consistent with this. Excuse me. So let me instead dot that. We'll dash it, actually, like that. There you go. So there's the path that the thing is going to take around in a circle. Here, we'll say. And so I'm going to locate it. Maybe it's a mass. So there's a little mass there as it goes around. As it goes around, it has a velocity. The velocity, remember, is at right angles to the circle. So this would be v right there. Okay, and here's r, locating this right here. Now that said, there are some unit vectors that we can look at here that are in circular polar coordinates. And there's one unit vector that points this way, and there's also one unit vector that points this way in the same direction as v. And so this one right here, we typically call r hat. R hat points along the direction of r, but it has a length of 1. This one right here, if you think about sweeping at an angle as you go around, this is in the direction of the angle that you're sweeping, okay? And as a consequence, we call that theta hat. And then you have z hat, which is, the one we're familiar with already. It goes up like that. So there's z hat right there. So what you have here is, an orthogonal coordinate system. If you were to draw these things like x, y, and z, and this is just a way to sort of keep things in your head with respect to what goes where. So you'd have z, theta, and r. So they form, an orthogonal coordinate system, just like what we're used to. So if you were to take and think about cross products, and what if I crossed theta hat into z hat? So theta cross z gives me r. Okay. Likewise, I could cross z hat into r hat. And if I do that, that gives me theta hat. Okay. Likewise, if I cross r into theta, I get z hat. Okay. So these are like cross product relationships between each of the coordinates, and this is one of the ways that you can define a coordinate system. Now that said, much like mathematics, when it comes to how something moves around in a circle, we look at the angle to give us a direction of, or a sense of direction rather. And in math, counterclockwise motion, which would be from x towards y, that's in the direction of positive angle. So if you want to think of an analogy with respect to one-dimensional motion, counterclockwise would be the same thing as plus x. Clockwise motion is negative. So if I were to go this way, that would be considered negative motion. Okay? Now, excuse me. So that said, the motion of the things that we look at when they rotate is going to be typically in a circle. And as a consequence, that means that the radius itself of the circle in magnitude is constant. Now, we're going to use this fact, and also the fact that since it's along the circle, the physical path that these things trace out is along an arc. The relationship between arc and the radius and the angle that's swept out is this right here. This is for arc length along a circle. Okay, so if we think about this and we think about the physical velocity, now I want to be clear. The velocity that I'm talking about here would be translational velocity. We think about the relationship between that and the angle that's swept out. Okay, looking here, right? If I took the derivative of the path with respect to time, this would be the same thing as the velocity along it. Okay. Now, so if I carry that derivative out, r comes out because it's constant since we're on a circle, which means that v would be equal to r times d theta dt. Now, theta is the angle that's swept out, and it can change with time. It's like a position coordinate. So if you take the derivative of a position with respect to time, you get a velocity. And since this is an angle, we say you get angular velocity. This right here is angular velocity. And we denote it using a cursive thing that looks like this. This is omega. Now, that said, let's look at the units. So first of all, theta itself, we think of as being in degrees or in radians. Now, in truth, degrees and radians are nonsense units. Theta itself really is unitless. We think of degrees and of radians just to give us an idea of what the number that we're looking at really means. But if you think about mathematical functions like the natural log, like e to the x, like sine, cosine, tangent, all these things are supposed to take unitless arguments. Okay? So in reality, theta itself is a unitless thing. So the units, keeping that in mind, for angular velocity is 1 over seconds. Okay, so this is the units of angular velocity. Now, so in this case, if you look at our physical velocity, and this right here we actually call tangential velocity. The reason why we call it that is because in this specific case, along the path of a circle that is tangent to the circle itself. Okay, so the velocity would be a tangent line, tangent to the surface of the circle, the path. All right. So, but we can also talk about acceleration, because we know acceleration is how your velocity changes with respect to time. And again, if you look at this right here, okay, r again is constant, comes out. This would be r times the derivative of the angular velocity with respect to time, or d omega dt. And sure enough, that's an acceleration. We call this alpha. It's angular acceleration. Okay, and it's measured in radians, or 1 over seconds squared. Okay. Now, so all the concepts that we came up with back in chapter 3, where you have average velocity, you have instantaneous velocity, you have speeds, you have all these things, they are one-to-one translatable to angular motion. For example, omega with a bar at the top would be an average velocity. Change in angle over change in time. Compare this to average velocity, which is change in position over change in time, along one direction. Instantaneous velocity look like that. So as long as you think of theta as being the rotational analog to position, okay, then all the stuff comes over. Acceleration, average acceleration, all these things are one-to-one transferable over. Now, that said, frequently it's useful for us to talk about relationships between, say, omega r and v, much like the one that we have right here. Right here. So if you think about it, v is this way, r is this way. And one way that we can sort of think of is omega as a vector, which it is the following way. V is omega cross r. Now, if we're dealing strictly with right angles, then V is just omega times r, because the angle in between is 90 degrees, and for cross products, sine of 90, well, that's 1. Same thing here. Okay. So what that implies is if you look at this and you think of V as being along this direction, omega is along z. Okay, and sure enough, as drawn, positive omega is up, negative omega is down. Up, going counterclockwise, down, going clockwise. So, how do you remember that? Well, there's this thing called the right hand rule. Okay, so let me still this, and I'm going to copy it and bring it over here. Okay, and I want you to take a look at the direction of R, which would be like being along A, the direction of V, which would be along B, and the direction of omega, which is along C. This follows a standard right-hand rule. Okay, so why is it called the right-hand rule? You take and you put your fingers in the direction of the first vector, in this case, A or R, and you close them. I don't know why I put R here. This should be V. You close them towards the second vector, which would be V, and your thumb gives you the direction of the third vector, which in this case would be omega. So as you can see here, there are a lot of sort of one-to-one transferences between translational stuff and rotational stuff. And because of that, what I'd like to do is to start a chart, sort of a table that's going to keep track of all this. So what I'll do is I'll put translation here. I'll put rotation here. And then I'll put concept here. And let's just sort of table it up here like that. Highly scientific looking. That's what it is. We'll add some more later on if we need them. So the first concept is position. From a translation standpoint, along one dimension, we used x, and for rotation, we're going to use theta. The next we had was displacement. And as we saw, where is it? Right here, you know, for example, with average velocity being, your change in position over time, and this being displacement, there's an analog here for rotational velocity. So this would be angular displacement. So with translation, we call it delta x. It was x minus x naught. And for rotation, we're going to call it delta theta, which surprisingly enough would be theta minus theta naught. The next one would be velocity. For translation, we had average velocity, which was your displacement over time. And then we had instantaneous velocity, which was the derivative of position with respect to time. And for rotation, we have your average angular velocity, which would be delta theta over delta t. And you also have omega, which is d theta dt. For acceleration, for translation, we have average acceleration, your change in velocity over time. And then there's instantaneous acceleration, which is the derivative of your velocity with respect to time. And for rotation, you may not be all that surprised to discover that you have average angular acceleration, which would be delta omega over delta t. And you also have instantaneous angular acceleration, which would be d omega dt. So as you can see, these concepts look the same. Okay, and the nice thing about that is that for pretty much this whole chapter, um, with the exception of two notable cases, everything that you see is going to be something that you've seen before. All you have to do is to make a change of variable. Okay, so for example, with rotation velocity, we're changing the variable of velocity to omega and the variable of position to theta. Okay, so all the stuff is the same. Conceptually, it's just a change of variable. Now, that said, let's do a few examples. A 12-inch record plays at 33 1/3 RPM. What is the velocity of a point on the record's edge and at the halfway point? Well, the reason why I wanted to work this example was to show the relationship between tangential quantities and angular quantities. Now, I want to remind you that we had come up with tangential velocity, and this relationship to angular stuff was r times omega. Okay. We also have tangential acceleration, and this relationship to angular stuff is r times alpha. Okay. That said, let's draw us a picture. Here's our record. Here's a coordinate system right here. Y and X. For the first part, this will be R, locating a point on the outer edge right here. And we're going to watch this thing, we'll say, go around this way, so it's positive. So what we're given here is that it's a 12-inch record. Now, 12 inches describes the diameter, so the diameter here would be 12 inches. Now, if you convert that to meters, let me see here, I did that earlier. Where's my work area? Oh, yeah. Here we go. It's 30.48 centimeters. So we're, 0.3048 meters, right? We're also given the angular velocity. Omega here is 33 1/3 RPM. Now let's talk about what RPM means. RPM means revolutions per minute. Now, one revolution from an angular standpoint is 2 pi radians, and we always work with radians when we're dealing with rotational motion. A minute, obviously, is 60 seconds. So taking 33 1/3 RPM and putting it into the MKS system means that we go from RPM to radians per second. Now, so 33.33 RPM, noting the fact that there are 2 pi radians for every 60 seconds in 1 RPM. Gives us let's see here. So times 2 pi. Where's my pi out there? And then divided by 60 seconds. So this is going to be 3.49 about radians per second. Now, let me take a moment to point out the fact that pi doesn't mean radian. I'm not entirely sure where this particular conceptual issue popped in. But I've seen people refer to 2 pi as 2 radians. Pi is not a radian. Pi is a number. Pi is 3.14 and some change. Okay? So, let's not forget that. Okay, now, so we have the diameter. We have the angular velocity. Now, let's not forget the radius is 1/2 of a diameter. All right? Now, we want to know what the velocity is of a point out on the edge is. That's for the first part. Well, v, which is your tangential velocity, is r times omega. Or, using this, would be 1/2 d times omega. Or 1/2 times 0.3048 meters times 3.49 radians per second. So, if you do that, you get 3.49 or 48 rather, divided by 2. I get about 0.53 meters per second. Now, I want to point something out here. Again, remember, radians and degrees are nonsense units, and you can actually see that here. What if omega was, in fact, measured in radians per second? Like this was a legitimate unit. Well, when you do this right here, you'd have meters times radians per second. That's not the unit of velocity. Okay, velocity is meters per second. So as you can see, by pointing out the fact that degrees and radians are nonsense units and basically just tell you what mode your calculator needs to be in, you end up with meters per second, which is what you want. Now, the next part says, what's the velocity of a point on the record's edge at the halfway point? So at the halfway point, it would be 1/2 of r. Okay, so here we want the velocity at 1/2 of r. Well, 1/2 of r would be 1/2 of 1/2 of d, or 1/4 d times omega. That means basically all you're doing is taking this and dividing it by 2. And if you do that, you get about 0.27 meters per second. All right, so let's do another example. An angle grinder has a cutting wheel with a radius of 8.0 centimeters and spins at 10,000 RPM. How fast does the point on the edge travel? All right, now, so again, we have something in RPM, which is a very common notation, or a very common, rather, unit that you see used to refer to angular velocity. Now, an angle grinder, for those of you that don't know what they are, look kind of like this. Let me find this one so you can see. Let's see here. This is what an angle grinder looks like. Now, these things spin super fast, and they have cutting wheels that you can attach to them that will just make short work of a lot of stuff. It's one of the reasons why I wanted to work this problem, is to show you that. So again, let's draw us a picture. This would be the disk from our angle grinder, and here is a little coordinate system centered on the center of that disk. Okay, and this would be a radius vector pointing to the outside part. Right here, we'll say, is roughly as this thing spins, but we want to find out how fast it moves. Thankfully, we know what the radius here is, right? So if we look at our givens, our radius is 8.0 centimeters, which is 0.080 meters. We also have an angular velocity here, our angular velocity here is 10,000 RPM. Now remember, to convert this, one revolution is 2 pi radians, and a minute obviously is 60 seconds. All right, so we want to do that conversion right there. And if I do that, I get, let's see, 2 times pi. Divide that by 60. I get about 1,047 radians per second. Okay, so we want to find the tangential velocity v. So again, v is equal to r times omega. R here is 0.080 meters. Omega is 1047 radians per second. And if you actually do that, that's about 84 meters per second. All right, now that's really fast. In fact, if you convert that to miles per hour, let's see, that's about about 188 miles per hour. Now, why am I pointing this out? Well, they always tell you that you should wear eye protection. And, a lot of these cutting wheels, when you cut with them, are made out of carbon fiber. So you can imagine one of these things coming apart on you while you cut and having it fly into your face. Those pieces of carbon fiber that are sharp enough to cut steel like it's nothing will be hitting you at almost 200 miles per hour. So, they will absolutely wreck you. So again, not a good thing. Now, so that said, what I'd like to do, at least initially, is to talk about situations where you have constant angular acceleration. Now, we'll relax this to some degree later on, okay? But much like when we first started talking about kinematics, we had to start easy, and that's what we're doing right here. So what that means is alpha, which you could think of as, again, the derivative of your angular velocity with respect to time. That means that this is a constant, okay? So long story short, we know that the average acceleration would be equal to the instantaneous acceleration since it's a constant, which is the same thing as your change in omega over time. So if you stick with the formalism that delta omega is omega minus omega naught, and that delta t is t minus t naught, but t naught is something that we generally set to be equal to 0, then what that means is that you can write this equation the following way. Now, if you solve for omega, you get this. Now, check this out. Look familiar? I hope so. It looks just like the first kinematic equation. And that's because this is the first kinematic equation for rotational motion. So, if I go back here and I look at the first kinematic equation, for translation, it's v is equal to v naught plus a times t. And for rotation, it's omega is equal to omega naught plus alpha times t. Looks the same. Okay? Now, that said, why don't we look for a second kinematic equation? Well, to do that, omega on average is equal to your change in angular position over time. So, an average omega would be your final plus your initial divided by 2. Delta theta is theta minus theta naught. Delta t really is just t. So if I move the t to the right-hand side, move the theta naught to the right-hand side, I get this. But look, this is omega right here. So let's plug that into there. And what we'll do on the right-hand side is we'll have an equation that deals with stuff that we know at the beginning plus the time in the future. So omega is omega naught plus alpha times t, and then we have to add another omega naught there, and then we're dividing by 2. Well, you multiply this stuff through, you group the omega naughts together, and you get something that looks like this. Oh, well, this looks really familiar. Are you telling me that theta is equal to theta naught plus 1 half alpha times t squared plus omega naught times t? Well, I sure am telling you that x is equal to x naught plus 1 half at squared plus v naught t. Oh, it's the same equation. All you did was to change the variables, like I said earlier. So, let's put another line here. And we're going to put the second kinematic equation. X is equal to x naught plus 1 half at squared plus v naught t for rotation. Theta is equal to theta naught plus 1 half alpha times t squared plus omega naught times t. Looks the same. It's the same thing. Okay? It's just now you're dealing with rotational stuff as opposed to translational stuff. Now, so I'll tell you what. Why don't we just save the rigmarole and do it this way? Do I need to prove that the third kinematic equation that we came up with, which looked like v squared minus v naught squared, is 2 times a times x minus x naught? Do I have to prove that it looks like omega squared minus omega naught squared is equal to 2 times alpha times theta minus theta naught? I hope not, because guess what? At the end of the day, it is. It's the same thing. It's pretty nice. Okay. So far, really, everything that we've seen is stuff that we've seen before. It's the same stuff. That said, why don't we work a few examples? A milling wheel has a radius of 1.5 meters, and it has an angular acceleration of 2 radians per second squared. If it starts from rest, what will the angular velocity, angular displacement, velocity of a point on its edge, and acceleration of a point on its edge be after 15 seconds? So let me give you an equivalent of this, minus the velocity and the acceleration part right here. A car has an acceleration of 2 meters per second squared if it starts from rest. What will its velocity be and its displacement be after 15 seconds? It's the same sort of problem. Okay, so let's draw a picture. Here's our milling wheel. Right there. It has a radius let's see. We are given the radius is 1.5 meters. the angular acceleration is 2.0 radians per second squared, not 2 pi per second squared. Remember, pi is not radian. It is a number. Second time I told you. Okay, so it starts from rest, which means that our angular velocity initially is 0. We also know we're looking for these quantities after 15 seconds. What quantities are there? What am I trying to find? I'm trying to find omega, which is my angular velocity, delta theta, which is my angular displacement, v, my tangential velocity of a point out on the edge, and a, my tangential acceleration of a point out on the edge. We have a picture, we have what we're given, we have what we're trying to find. What do you do next? You write out your kinematic equations. There's one. There's another. Oop, not omega. And there's your last. The next thing you do is to simplify. And we'll have our angle start off at 0 when it first starts to rotate to make our lives easy. Omega naught is equal to 0, theta naught is equal to 0. That's 0, that's 0, that's 0, that's 0, that's 0. Okay? So at the end of the day, you have omega is equal to alpha times t. You have theta is equal to 1/2 alpha times t squared. And this is really the same thing as displacement since our starting position is 0. And then you have omega squared is equal to 2 times alpha times theta. Okay? So things have simplified greatly. And it's almost identical, like I said, to just a simple one-dimensional car problem. All right? So we're gonna start first. Well, we have enough information here to start with omega, or we could do theta. So why don't we just do omega first? So our angular velocity after 15 seconds is going to be alpha times t. And alpha is 2.0 radians per second squared. T here is 15 seconds. So 2 times 15 is 30. That's 30 radians per second. Okay, so there's our angular velocity. The next thing we're going to find will be theta. Theta is 1/2 alpha times t squared, or 1/2 times 2.0 radians per second squared times 15 seconds squared. Well, the 2 and the half kill each other off, so it's really just 15 squared, which is 225. 225 radians, or you could say RAD, just to show that it is in fact in radians. But you don't have to put that. Okay? Now, in sig figs, I'm seeing 2. $230 radians. One of the few times in which you can write a number down and not have to put units. So that takes care of that. That takes care of that. Why don't we find v next? Well, v is your tangential velocity, and it is equal to r times omega. R is 1.5 meters. Omega after 15 seconds is 30 radians per second. So 1.5 times 30 is 45. 45 meters per second. That's your tangential velocity. Now, what about your tangential acceleration? What kind of acceleration did it have while it was doing this? Well, that's r times alpha, or 1.5 meters, whoops, not meters per second, times 2.0 radians per second squared. Well, 1.5 times 2 is going to be 3. So 3.0 meters per second squared. So not bad. Really, the only new stuff that you have to deal with, if you're presented with the situation of even having to deal with it, is going from the angular stuff to this tangential stuff. Okay, let's work another example. A sphere of radius 2 centimeters goes from 20 revolutions per second to 0 in 30 seconds. What is its angular acceleration, and how many rotations did it go through in this time? Here's your sphere. Okay, there's some coordinates, freehand r. So there's r right there. Now, so we're going to assume that it was rotating this way. So if you think about rotating this way, that's the same thing as going in the positive direction along x. So if you had something going this way along x and you had to push on it to slow it down, wouldn't you push on it this way? Remember arguments that we made about the direction of acceleration way back when. It's along the direction that you would have to push something in order to get it to do what you want it to do. So here, if this thing is rotating this way, if I wanted to slow it down, wouldn't I have to spin it this way or put my hand on it to sort of turn it this way to get it to slow down or accelerate it this way? Yes. So this is going to be the direction of the acceleration. It's going to be negative. Now let's see if that's the case. So we're given here the radius of our sphere is 2.0 centimeters. That would be 0.020 meters. We're given an initial angular velocity that's not 0, but that's 20 revolutions per second. That would be 20 times 2 pi radians per second, or 40 pi radians per second. You have to put this in your calculator. You have to put 3.14159 and all that stuff in there to get it to do its thing. All right. Now, your final angular velocity is 0, and it takes you 30.0 seconds to slow down. I want to know what the angular acceleration is and how many rotations it goes through in this time. So I want to find, what am I writing given there? I want to find alpha and delta theta. Well, we're going to assume, like before, that our initial angle is 0. Just make our life easy. So let's write out our kinematic equations here. Omega is equal to omega naught plus alpha times t. We have theta is equal to theta naught plus 1/2 alpha t squared plus omega naught times t. Plus we have omega squared minus omega naught squared is equal to 2 times alpha times theta minus theta naught. So, what do you want to find first? Alpha, delta, theta. I'm going to propose that we find alpha first. We're going to need it. But before we do that, excuse me, let me plug in my zeros here. So my final angular velocity is 0. My angular position initially is 0, and that's 0. And that's 0 as well. So I propose we use this to find the acceleration, and then we use this to find theta. All right. So here, this looks like 0 theta. 0 rather is equal to omega naught plus alpha times t. So if I solve for alpha, it's equal to minus omega naught over t. Omega naught is 40 pi radians per second squared, or radians per second rather. And t is 30 seconds. So you can see here you got a negative sign out in front. And like I'd argued out before, as drawn, our acceleration should be negative. So when I do this, I get 40 times pi divided by 30, 4.19 radians per second squared. So there's our acceleration. Oh, let's see, 1 sig fig, 2 sig figs, 3 sig figs. So I guess 4, huh? So that takes care of that. Next, we have delta theta. I wanted to use this to get that. And if I solve for theta there, since our initial theta is 0, I get minus omega naught squared divided by 2 times alpha, which would be minus 40 pi radians per second squared divided by 2 times alpha. Alpha would be, oh, there's a minus sign here, minus 4.19 radians per second squared. As you can see, the radians per second squared cancel each other out, and you get something that's unitless, which is what you expect here. So let's see here. 40 pi. You got to square that, then divide it by 2 times 4.222. I get 1,884 radians. Actually, 885. Now, but we want rotations. Okay. So one rotation is 2 pi radians. So if I were to take this and divide it by 2 pi, I get 300. So there's your answer right there. Now, so as you can see, these problems are almost identical to one-dimensional motion that we learned back in chapter 3. That said, one big application that you see for this sort of stuff is something called rolling without slipping. Okay, so a good example of this would be a car. Its wheel, assuming that you hit the gas and you don't spin out. What happens is as the wheel rolls, what it does is to roll its circumference out on the ground. So, sort of draw it like this. There we go. So here's the center of our wheel right here. And what I'm going to do is to sort of draw a coordinate system centered there. And this is the point that our wheel rotates about, whenever it goes. So as the wheel rolls this way, what happens is the center of the wheel moves this way. And it moves this way at the same velocity that a point on the outside of the wheel does. Okay, so here, your tangential velocity, which I'm going to call v sub t, and the actual velocity of the wheel are going to be same in magnitude. As your wheel accelerates, the tangential acceleration that it experiences is the same in magnitude as the actual acceleration of the center of the wheel as it goes. And that's because it's connected to the ground. As it rolls without slipping. So as it goes this way and traces out one circumference, the center of the wheel also goes one circumference. And what that does is to tie the velocities and the accelerations together. Okay, so, and this is a pretty big deal because if you actually put a lot of thought into how your wheel is able to do its thing and make your car go forward, everything involves rotations. So the pistons inside the engine, as combustion happens and pushes them down, they're attached to something called a crankshaft, and the crank has got lobes on it that might look like this if you were to look straight down into it, and that's where the pistons are attached. And what they do is they cause this to rotate. They cause the crankshaft to rotate. And that rotation through the crankshaft is usually attached to a transmission. In a rear-wheel drive car, the transmission has got a bunch of gears in it, and what they do is to through rotation, either make one rotation of the engine be more than one rotation of what goes out of the transmission, or less. That would be the difference between first, second, and third, and fourth gear, and whatever else your car does. Well, all this is attached at the end of the transmission to what's called a drive shaft. The drive shaft spins like this and is attached to the rear axle. And this right here comes out. That's what you see there. That's your rear axles right here. And there's gear work in here so that as this rotates, it takes this rotation right here and makes it like this. So all this is rotation. So your engine works off of basically rotational motion. And that rotation, that's the reason why your wheel rotates. So as your wheel rotates, you put it on the ground, and what that does is you take that rotational motion and put it in translational motion. Okay. So like I said, rolling without slipping is a big deal. So as an example, let's work this example. You have a car's wheel. It has a radius of rather of 75 centimeters. If the car starts from rest and accelerates at 2g for 10 seconds, what I want to know is what's the angular acceleration of the wheel? How many rotations did the wheel go through in this time? And also, what is the velocity of the car and the angular velocity of the wheel? Okay. So what I propose to do is to, we're going to draw two pictures here. We're going to draw one of the car itself and then one of the wheel. So here's the car. Okay. It has an initial velocity that's 0. That's the same thing as saying that your angular velocity initially is 0. Okay. Now, so your car has an acceleration A of 2g. And let's not forget that g is the same thing as 9.8 meters per second squared. Okay. It's going to accelerate. It gets out over here somewhere, and this is 10 seconds down the line. And like I said, what I want to know is what's the angular acceleration? How many rotations did the wheel go through in this time? And what is the velocity of the car and the angular velocity of the wheel? Okay. So if we think of this as being the ground right here, as the wheel rotates, it's going to rotate clockwise. And what that means is that our omega and our alphas are going to both be negative. Remember, counterclockwise motion is positive. Clockwise motion is negative. Okay. So what are we given? We're given the radius of our wheel which is 75 centimeters, which is the same thing as 0.75 meters. We're given an initial angular velocity of 0, an initial velocity of 0. We're also given an acceleration of 2g, which is the same thing as 2 times 9.8 meters per second squared, or 19.6 meters per second squared. We're also given that we want to find all this stuff at 10 seconds. So what I propose we do, like I said, is to work this problem. And then once we get our information from here, let's work on the rotational aspect of it. Okay? So we want to find alpha, delta theta, v, and omega. Now, v is going to easily come from just working this problem right here. So let's do that. We have our kinematic equations for translational motion, which looks like this. Let's go ahead and make theta naught equal to 0 and x naught equal to 0. In many ways, I guess that almost should be taken for granted, but not. We have an initial velocity of 0, which means our kinematic equations here give us v is equal to a times t, x is equal to 1/2 a times t squared, and v squared is equal to 2 times a times x. So let's find v first. And to do that, I propose we use this. So v is equal to 19.6 meters per second squared times 10 seconds. So you put your numbers in. This is 196 meters per second. But we also know that this is the same thing as r times omega. So now we have our omega. Okay, so 2, 3, or this is actually 1 rather. So there's v. Here, omega is v over r. You take and divide that. 0.75, 261 radians per second. Or, again, to 1 sig fig, about 300 radians per second. So that takes care of this, and that also takes care of this. We also have an extra bit of information. So that's taken care of. We've got all our translational quantities that we need. Now let's do the rotational stuff. All right, plug in our initial conditions. That's 0, that's 0. Our initial velocity is 0. Whole bunch of zeros there. And, what do you want to find? Well, we need to find alpha. We need to find delta theta. We can use this to find alpha. If we use that, alpha would be omega over t, because we know omega is 196, or rather 261 radians per second, and the time is 10 seconds. So that ends up being about 26.1 radians per second squared. Okay, or if you round it again, to 1 sig fig, about 30 radians per second squared. So there you go. So that takes care of that. Now we have delta theta. We've got a couple different ways we can find it. Let's use this, because since our initial velocity, or initial rather position, is 0, theta here is the same thing as delta theta. Theta would equal 2 omega squared over 2 alpha. Omega is 261 radians per second. That's squared over 2 times alpha. Alpha is 26.1 radians per second squared. So let's see. Let's see here. Square that. And then divided by 2 times 26.1. So I get 1,307 radians. But remember, we're looking for rotations. And there are 2 pi radians in one rotation. So if I divide that by 2 pi, I get 208. Or if you keep to sig figs, about 200 rotations. So that's rolling without slipping. All right. Now, what if you're rolling with slipping? Oh boy, then you got trouble, because you don't have a clear relationship between the rotation of this thing and how it goes forward. You would need to know that relationship in order to move forward with it. Okay, you'd have to be given that, or you'd have to be able to measure it or determine it somehow. Okay, so like I said, this right here is the beginnings of rotational motion. Now, what I want to talk about next class is going to be we're going to talk about energy. So we're going to start talking about kinetic energy, specifically rotational kinetic energy. And that's going to introduce our first real new rotational concept. And that's the concept of the moment of inertia. And I'll see you then.